Today we're going to go over the structure of water and how that structure of water leads to the amazing properties of this molecule that life wouldn't exist without. So if we start off basically with our actual water molecule, which you need to know for your quiz and be able to draw, water is H2O. Right, and that molecule is going to be made out of one oxygen molecule that's bound to two hydrogen molecules. All right, so that's our basic shape for oxygen. Now with that, we have this here, which is a polar covalent bond. That polar covalent bond, as we talked about the other day, this idea of a covalent bond, they are going to share their valence electrons, but it's called a polar covalent bond because when that sharing happens, now this is not how electrons orbit the two, but that oxygen is kind of a hog and it holds onto those electrons more often. So what happens, because we know that this here, the electron has a negative charge, and same thing will happen with the electron it's sharing with this hydrogen here. So you'll notice that all of a sudden these electrons are spending a lot of their time around this oxygen. So with that, this side then becomes slightly negative. Because as those electrons hang out here, this side picks up this slight negative charge. And over here, we're going to get a slight positive charge. Same thing with this hydrogen over here. We'll get a slight positive charge. So at this point in time, our oxygen molecule, which has become slightly messy, has then these sides. And that's what polar means, is sides. So think about like the North and the South Pole. Once we've established this, this molecule has sides. We've got a negative side and a positive side. Now these charges aren't full charges, but again we now have this basic structure of water molecule, and again it's a polar molecule giving these sides. Now once we have, you can see here we have two water molecules. From this polarity of water, as we just described, here's my water molecule. This oxygen's holding on electrons more often than these hydrogens, so I have slightly negative, slightly positive. Well, this molecule of water is doing the exact same thing. So now we have this hydrogen here that is slightly positive and this oxygen that's slightly negative of separate water molecules. So these opposite charges then attract with one another. So they create this temporary bond here that's called a hydrogen bond. So again, right here, we have a hydrogen bond. And what I like to call, it's almost like a handshake. They're happy to see one another. They shake hands. It's something that will hold them close together, but it's not a permanent bond. And as we go through and add in millions of water molecules, they're constantly shaking hands and saying hello to one another. And that's, again, we go all the way back to the fact that this is a polar molecule. Negative side, positive side, so that allow it to hold on here. So if we add, we could have then another water molecule down here. Again, that will be slightly negative. So if we go, and it's going to form then a hydrogen bond here. So again, with thousands of water molecules, they're all constantly shaking hands with one another, holding each other as a group. Now if we take and remove my sloppy drawings, here you have a nice rendering of what happens with that water. So again, each water molecule here, you can see that oxygen, which is going to be slightly negative, and all these hydrogens that are slightly positive, and they form these handshakes between all these water molecules. Again, imagine that with all those water molecules, you have then these molecules that are going to hold on to themselves. That attraction is called cohesion. Right? And that becomes really important, this idea of cohesion. So water sticking to water is called cohesion. And if you remember earlier in the semester, we talked about how co means together. So hesion is going to be to stick, co is together. So you've got to know that water sticking to water is going to be cohesion. And in physical science, when you did the experiment where you put the drops of water on the penny and you got this nice big bubble on top, or it's the same idea if you fill the glass with too much water, before it spills you get that nice dome. Well, that's because the water molecules are holding on to each other to keep their buddies from falling out. Now after that cohesion, we have a property called adhesion. Adhesion is when when water is going to stick to another substance. So glass. This is why when untreated glass, water doesn't bead up. It actually kind of spreads on that glass because the water grabs onto that glass and it's attracted to that. Now, for that to happen, our water has to bond to something that is also polar. Because that water molecule has those positive, negative sides, it needs somewhere to attach. So if there's a molecule that doesn't have sides, and those molecules are called nonpolar, if they don't have sides, there's nowhere for that water to attach, and they won't interact together. And that's like oil. So you can see here, oils and wax. So when we dump water or oil into water, it'll bead up and it won't mix. You see that in salad dressings where you get your layer of oil and your layer of vinegar because vinegar is water soluble. So we get that non-mixing. So non-polars do not interact with polar. Again, because that polar has sides, pluses and minuses. This has no sides, so there's nowhere for that to go through and attach. And that's really important when it comes to what water can dissolve. One of the properties that cohesion of water causes, so water sticking to water, is a property called surface tension. So water holding on to water creates this tension on water. So bugs like this one here can walk on water. This is also the same idea that when you do a belly flop on the pool, it hurts so much because you've got to break all of those hydrogen bonds. Now you yourself can't go and walk out on water because you're too heavy and the hydrogen bonds aren't strong enough. Remember, they're handshakes. They're weaker bonds than covalent and ionic bonds, so they do have their limit. But smaller bugs like this, or things that can spread out their weight through surface area, are going to float like a leaf floating on water. But again, we really feel this when we go and jump into a pool, this water holding on to water. Just a quick visual. I had mentioned on the other slide how polar and non-polar molecules do not interact. So here we have oil on top of some water. Again, water is that polar molecule. This here is going to be then oil, which is non-polar, and oil is less dense than water, so water's on the bottom, oil's on the top, and they will not mix. We can shake this up and they'll kind of mix together, but we let it sit, it's going to go through and separate. And again, last year in physical you did this with the tube that had the blue and the yellow solutions. You shook it up, again like salad dressing, so it will mix a bit, but at the end of the day they're going to separate out and create these nice layers. A unique property of water is called capillary action. Here you can see a cross section of a tree, and you can see they have these little tiny microscopic, they're almost like straws, they're tubes. What happens is both the adhesion and cohesion properties of water allows water to travel up these tubes. So water starts in the bottom in the roots into the tubes. It has adhesive properties to the inside of this tube, and as one begins to climb up, it actually pulls its buddy from behind because of cohesion. So with both of those being used in these tubes, it helps get water to the top of trees, which was a problem and scientists couldn't figure out for a very long time. So what happens actually is up here in the leaves, it's a process called transpiration. And a way to think about it is almost as if the plants sweat. So there's water evaporating out of the leaf. And as that leaves the leaf, it's kind of like jumping off. And as it does that, it grabs the water molecule behind it. And as it goes through, it pulls water all the way up these stems and these trunks from the roots. So you have this nice consistent pull as water evaporates out the top. Without cohesion and adhesion, that would never be helpful. So capillary action becomes really important for trees to get water all the way up to the top. They need that water for photosynthesis up here so they can make their sugars and live. Another property of water, and you guessed it, this goes back to the hydrogen bonds of water, is a high specific heat value. With water, you can see here, I think we all know that idea that if we take a pot of water and boil it, it takes a very, very long time. Well, the one reason is because water does a very good job of absorbing energy, absorbing that heat, and actually not changing temperature. So with that, the reason is, again, if you remember, the energy of molecules move around. They have kinetic motion. So as we increase the temperature, the molecules move around faster. And that's an idea you've got to understand throughout the whole semester. So as we go to begin to heat these up, the molecules want to move faster. But if you remember, we said hydrogen bonds are like handshakes. So as they try to move faster from one another, they also are still excited to see their friends, so they shake hands. So it becomes very hard to get these molecules to move quickly while they're trying to shake hands with everybody. So water does a very good job of absorbing all of this energy and actually not changing temperature. This becomes very important for our planet because our planet is hit by a lot of energy from the sun. While being the 2/3 of our planet is oceans, they actually can absorb that energy from the sun, and it stabilizes our Earth's temperature. So that kind of idea of a stable temperature is important. Organisms are primarily water. So as you go through and become more active and do lots of chemical reactions, you're actually releasing heat. But your body temperature doesn't change the way it would have without water, because that water has that ability to absorb lots of that energy without changing temperature. So that high specific heat value becomes important for stabilizing temperature, not only for our environments, but also for the organisms. Another way this property of high specific heat helps organisms in us is it actually helps us cool down, because it does take a lot of energy to get water to speed up and eventually speed up so much that it's going to evaporate. So when our bodies begin to heat up, we begin to sweat. That sweat's primarily water. That water is going to lay on our skin. And actually, as the molecules of our skin are vibrating and they're increasing their vibrations because our temperature goes up, that water that's sitting on top of our skin is then going to absorb that energy from those molecules that are vibrating, and they're going to start vibrating faster to the point where they'll leave our skin, and in doing so, that's going to remove heat from our skin, and that's going to cool us off. And it doesn't have to be sweat. You can get out of a pool, you can be rained on, it can be getting out of the shower. You have organisms that go through and wallow in wet mud or get into a river. So all of these things are going to help cool off organisms, and it goes back to that idea of that high specific heat and evaporative cooling for organisms. While we've talked about all these properties of water, one of the most unique properties of water is the fact that it floats when it freezes. Most molecules, and if you think about back, we just talked about temperature, when things get cold, what's going to happen is those molecules are going to slow down, and in doing so, they become much, much more dense. They compact together. Well, most molecules that happens to, but water, again, is unique because as it actually cools down, these molecules spread out from one another. So the way I like to envision it is if we go back to our room full of people who are moving around rather quickly and shaking hands, as I begin to slow them down, when they're shaking hands, they actually have that ability to then extend away from one another because they're moving so slowly. And if you imagine a room full of people doing that, moving so slowly, they go to shake hands and they can push back. And if everybody pushes back in the group, the whole group is actually going to expand and take up more space. At that point in time, that water has become less dense, so it actually floats on top. Again, a very unique property of water. And as water chills, it reaches a temperature of about 4 degrees Celsius, and that's when it's densest. So to begin with, we just slow them down a little bit. They're moving around. They do get kind of closer together, and that becomes dense. So our 4 degrees Celsius water would kind of reach down to the bottom here of this beaker. As it would actually get colder to 3 degrees Celsius and 2 degrees Celsius, it actually would make its way back up to the top, and then it would freeze at the top and stay at the top. So if this was kind of like a little pond, again, that water would get super cold. It would come down to the bottom, and at 4 degrees Celsius, it actually would start to then push out from one another. That's going to bring the water back to the top. It's going to finish freezing at the top, and then doing so is going to create this insulating layer right here on the top. So it'll stay there, and that's going to help preserve the life of the aquatic organisms that are down underneath. If it was the opposite and water became more dense, it would freeze across the top. Once it froze across the top, it would then sink if it was more dense. The next layer would go and it would sink, and from the bottom up, we would go through and create solid ice. What's left over then is actually this water, if there were land over here, would be pushed onto the land. This whole ecosystem would crash, and we wouldn't have life. And since life started in the oceans and in water, we wouldn't be here. One of the last things is, water is a great solvent. Sometimes you hear it called a universal solvent. So water has that ability, and you can see it here with the chloride. Now this is sodium chloride, so that's your regular salt. We know that when we put salt into water, it's going to dissolve. The way water dissolves stuff is because of its polarity, it has the ability to essentially surround anything that has a charge. So these are polar molecules. This is an ion, so it's a full negative charge. So you'll see here that there are hydrogens all the way around that surround that, separating it from our sodium, which is positively charged and surrounded by oxygens. They're now separated, they're dissolved. So anything that has a charge, water has that ability then to separate from one another, making a great solvent. If we wanted our salt back and we dissolve it, pretty much we know that all we have to do is go and boil our water. That causes the water to leave. And without these kind of protective shells around the outside, the sodium and the chloride can get back together. We have that wonderful salt that makes our fries amazingly tasty. That wraps up our basic structure of water. And again, it all goes back to this polar molecule. Without this polar molecule, water would not have the properties that it has, and that is related then to these hydrogen bonds. So at the end of the day, if you ask why water is adhesive and cohesive, it's because it hydrogen bonds. Why is it so hard to heat the water up? It's because of the hydrogen bonds. Again, they're holding hands. Those molecules are kind of holding on to one another. So, and all of that is in relationship to the fact that this oxygen hogs the electrons, and these hydrogens then become slightly positive. This becomes slightly negative.